Welcome to the Survival Historian, where the grit of survival meets the depth of forgotten knowledge. I'm your host, and today we're journeying into a realm of architectural genius that history almost let slip through its fingers. What if I told you that the most sophisticated shelters ever engineered weren't built with steel, concrete, or even stone, but with plants, carefully selected, meticulously prepared, and woven with such precision that they could outlast modern construction? We're talking about permanent structures that defied hurricanes, endured decades of use, and left archaeologists stunned by their durability. This isn't primitive survival, this is indigenous engineering at its apex, and it's time we unearth the truth. For generations, Western narratives have painted early human dwellings with the broad brush of simplicity. Crude shelters of sticks and leaves, temporary refuges that barely kept the elements at bay. The caveman stereotype persists in textbooks and popular imagination, reducing millennia of human ingenuity to cartoon illustrations of hairy figures huddling under rocks. But this narrative crumbles when confronted with the archaeological and ethnographic record. Indigenous peoples across continents were not merely surviving. They were engineering permanent architecture using sophisticated understanding of materials science, structural mechanics, and environmental adaptation that would make modern engineers take notice. These weren't flimsy huts that collapsed with the first storm. These were homes that stood for generations, built entirely from the fibrous heart of the plant kingdom. The foundation of this architectural revolution lies in the careful selection of specific plant species, each chosen for properties that rival synthetic materials. Consider bamboo, a grass that possesses compressive strength comparable to concrete and tensile strength approaching that of steel. Its hollow, cylindrical structure creates a natural I-beam, distributing loads with engineering efficiency that modern architects spend years studying. In the volcanic soils of New Zealand, Maori architects turned to harakeke, the native flax whose sword-shaped leaves concealed inner fibers of remarkable tensile strength. The extraction process was itself a feat of materials science. Leaves were carefully split, scraped, and processed to reveal muka, fibers so strong they could lash together entire structural frameworks. These weren't simple ties, they were engineered connections that allowed controlled movement in seismic events, a principle modern earthquake-resistant design has only recently rediscovered. Across the Pacific and into the Americas, palm fronds became the roofing material of choice, not through random selection, but through generations of empirical testing. The waxy surface of dome palm and iroquois palm leaves creates natural waterproofing, while their layered structure provides thermal insulation that keeps interiors remarkably cool in scorching climates. The selection extended to grasses and reeds harvested from wetlands, tuleraupo and specific species of Cymbopogon, each gathered at optimal growth stages when their silica content provided maximum rigidity and pest resistance. But perhaps most overlooked were the binding agents, the inner bark of cedar trees, processed into flexible yet incredibly strong cordage, the sinuous vines of acacia and gruyere species. Their cellulose structure evolved for exactly the kind of tension-bearing roles indigenous engineers required. Willow branches, harvested in spring when sap flow made them maximally pliable, could be bent into structural curves that modern laminated timber struggles to replicate. The transformation of these raw materials into permanent shelter required weaving techniques of breathtaking complexity and engineering precision. This wasn't, basket-making scaled up. This was structural engineering expressed through fiber. The fundamental techniques, twining, coiling, plating, each served specific architectural purposes that reveal a deep understanding of load distribution and material behavior. Twining created the primary structural framework, with processed fibers twisted around vertical posts in patterns that locked everything into a unified whole. The genius, honestly, lay in the geometry. diagonal wrapping patterns created triangulation, which is the most stable structural configuration known to engineering. Each wrap distributed loads across multiple points, preventing the catastrophic failure that occurs when a single connection bears too much weight. Watch closely and you'd see builders adjusting tension with practiced precision, creating joints that were rigid enough to support weight, yet flexible enough to absorb the shock of wind gusts or ground movement. Roof construction showcased coiling techniques where bundles of grass or palm fronds were wrapped in ascending spirals, each layer overlapping the one below in carefully calculated increments. The result wasn't merely thatch. It was a composite system where the outer layer shed water while inner layers provided insulation and structural continuity. The angle of installation mattered enormously. Too shallow and water-pooled, too steep and wind could penetrate, and indigenous builders had this geometry perfected through generations of refinement. Wall panels employed plating, where strips of bark or processed leaves were interwoven in over-under patterns that created surprisingly rigid surfaces. The three-dimensional structure trapped air for insulation, while the tight weave blocked wind and rain. When combined with wattle and daub construction, where woven panels were infilled with clay-based plasters, the result was walls with thermal mass, moisture regulation, and structural integrity that, honestly, modern synthetic panels struggle to match. The proof of this engineering brilliance exists in the archaeological record and early colonial accounts. Spanish explorers in 16th century Florida documented Timucua structures that had stood for decades, their palm-thatched roofs still shedding rain effectively. Archaeological sites in New Zealand reveal post holes and preserved cordage from ware that served multiple generations. These weren't temporary expedients. They were permanent addresses, homes where families were born, lived, and died. The sustainability of this approach, really transcends modern green building rhetoric. These structures were built from annually renewable resources harvested without depleting plant populations. Bamboo, for example, reaches structural maturity in just 3 to 5 years. Palm fronds regrow continuously and grasses return each season. The entire material stream was regenerative, requiring no fossil fuels, no industrial processing, and no toxic adhesives. When a structure reached the end of its life, it composted back into the soil, completing a cycle that left no toxic legacy. Today, architects are rediscovering these principles under the banner of biomimicry, but honestly, they're merely catching up to knowledge that indigenous engineers perfected millennia ago. The techniques offer profound lessons for a planet desperate for sustainable construction alternatives. This knowledge became forgotten not through the passage of time, but through deliberate marginalization. Colonial narratives dismissed indigenous architecture as primitive because, acknowledging its sophistication would undermine justifications for displacement and cultural erasure. Western architectural history elevated stone and metal while ignoring engineering expressed through organic materials. The result was a catastrophic knowledge loss as traditional practitioners were displaced, their techniques dismissed as irrelevant to modernity. But the resurgence of interest in sustainable building, coupled with growing recognition of indigenous knowledge systems, is finally changing this narrative. Researchers are documenting surviving techniques, architects are consulting with indigenous builders, and a new generation is learning that true innovation often means looking backward to move forward. These ancient weaving techniques offer more than just construction methods. They represent a worldview where human shelter exists in harmony with ecological systems rather than in opposition to them. They prove that sophistication isn't measured in synthetic materials, but in a deep understanding of natural ones. If this glimpse into forgotten ingenuity has sparked something in you, if you're ready to dive deeper into how human resilience and historical wisdom intertwine, then join the Survival Historian community. Hit that like button, share this video with anyone who believes that true innovation requires looking at what we've left behind, and subscribe so you never miss our explorations of how history, survival and endurance come together to reveal truths that modern life has obscured. The past isn't primitive, it's a masterclass in living that we're only beginning to understand. I'll see you in the next one.